Alright, let's turn next to problem set 6, which is a two-sample t-test assuming equal variance. But we don't see there a data set, so we have already given some summary statistics. But maybe at the end of the video, I use the summary statistics just to create some fake data sets in order to show you the same, but that's more of a voluntary exercise. It's like basically what I want to show you is how we can do a Monte Carlo simulation. But anyhow, let's just get started with that problem set, and we have two groups and they have certain characteristics. So we have mountain people and we have valley people. And so we collect the data on them, and that data is, so we have a statistic maybe. So N is, we have 25 mountain people and their mean height is 175 centimeters. With a sample variance of 81, and then we have a sample of 30 valley people, and they average out to a height of 180 and a variance in the height of 64. So this is the data that we have, and now we want to compare whether there is a difference. So first, graphically, actually we can already start with the solution here. So well, the first one, is it a T or C? Well, we don't know nothing about the population, so this is clearly a case for a T distribution. Okay, how many degrees of freedom do we have? In this case, it says here N1 plus N2 minus 2. So that is degrees of freedom. That would be equal to 55 minus 2. So that would be 53. And so degrees of freedom, that would be formally 25 plus 30 minus the two estimated statistics that we test for. So the degrees of freedom is 55 minus 2 equals 53. And so now, if I want to test for the difference, it seems that valley minus mountain, it's a difference of 5. And what I want to test for is a one-tail test, which states that the mountain people are statistically significantly smaller than the valley people. So I would actually test for whether the -5 is statistically significantly different from 0. So that's what we do. So because we say the mountain height is statistically significantly less than the valley height. Okay, so in this case, we are assuming a sampling distribution where we hypothesize that the difference, we hypothesize that valley, actually mountain minus valley, let's write that here, mountain minus valley, So that difference is 5, but here we assume H0, that mountain minus valley, is actually equal to 0. But then our sample suggests that the mountain people are on average 5 centimeters shorter. So we have here our sample average, which is -5. So now we want to know, is this statistically significantly different at the alpha of 5%? And for this we need to know the test score and the critical score. Well, because we already know the degrees of freedom and we know we do a one-tailed test, I can identify the critical T easily as the T critical, and that is so T critical. So for this we use again the formula T.inf inverse, and because it's a one-tailed test, all the 5% is in one tail, and the degrees of freedom is 53. And then we get a critical value and rounded to 3-digit of -1.674. 674. Okay, in a case like this, what's a little bit problematic is the standard error, and we need the standard error in order to calculate the test statistic. So we need to first calculate the pooled variance. Okay, so let's do that next. Pooled variance. So we use this formula. So that's given, there's no need to memorize that one. So that is equal to the degrees of freedom associated with the mountain sample, so that's 24, times the variance, which is the 81. Plus the degrees of freedom associated with the valley people, that's 29, times their variance, which is 64, divided by the degrees of freedom, which is the 53. So now we get a pooled variance of 71.698. But again, here the critical T was minus 1.674, and the pooled variance is 71.698. Okay, so now what's the standard error? So the standard error draws on the pooled variance, and let me just check again if that all looks correct. 24 plus 29, and the variance B4 and C4. Okay, that looks correct. So now the standard error is defined as the square root of the pooled variance divided by the number of observations in the mountain group, so that's divided by 25, plus the pooled variance divided by the number of observations in the valley sample, which is 30. And now we get a standard error of 2.293. That looks weird. Okay, So now we can calculate the test statistic. So we have to look at a -5 is how many standard errors away, or a sample that generates a difference of -5 out of a total of 55 observations, 30 in the valley, 25 in the mountain, you know. So what's the probability that you can get a difference of -5 when presumably there is no difference in the population? And again, if that has a very low probability, we reject. And to get to the probability, we need to first calculate the test statistic. And that would be our -5. How far is that away from the 0? Well, -5, so we don't have to write -0, divided by the standard error of 2.293. And so that will then be our test statistic. T test equals -5 divided by the standard error. And this is -2.18. So that is clearly in the rejection zone. So that means that our value of -5 corresponds to a test statistic, which is -2.818. And that is clearly in the rejection zone, because the rejection zone starts at -1.674 to the right. I mean, to the left. So the test statistic is -2.181, which is further to the left than the -1.674, our critical T. So therefore we reject the null. So the conclusion is reject H0. But we could have made a type 1 error, because, well, it could be that there is no difference between the mountain people and the valley people. And now we still have to calculate that area here to the left of test statistic of -2.18. And we don't have to multiply times 2 because it's a one-tailed test. So the p-value is equal to t dot dist, open parentheses, the -2.18, we have 53 degrees of freedom, and I want it cumulatively. So there's a probability of 0.16, 0.01, well, if we round it, 7 roughly. So this p-value is 0.017. So there's still roughly a 1.7% chance that we made a type 1 error. Okay, so I hope I didn't do a mistake, but this is how we would solve it. And now I just want to show you quickly, let's say we want to pull up the data analysis version in Excel. That would require that I enter the data range for value 1 and value 2. So what I want to do now is I want to simulate 25 observations for the mountain people that have a mean of 175 and a variance of 81, or a standard deviation of 9, and the same for the valley people. So, okay, so first I create observations, and I create quickly a list from 1 to 30. So we go to Home, Edit, Fill, not justify, edit, fill series, and I want to stop at 30. And then the mountain people, I will have 22 observations, and for the valley people I will have 30. So okay, so now what we can do also is we can go to data, and this is a little bit advanced stuff, so if all you are interested in calculating the hypothesis test, or this is already clear, this is just like an additional Excel exercise basically. So we can go to data analysis and we can say generate a random number. Okay, so the number of variables that I want is 1. And how many random numbers do I want? I want 25 for the mountain people. And the distribution should be coming from a normal, where the mean is 175, and the standard deviation is the square root of the variance, so that's 81, square root, that would be 9. And I want to put them right here, where the first observation is for the mountain people. And again, if you want to have the random seed again and want to replicate and get exactly the same numbers as I do, the random seed that I choose is 42, because 42 is the answer to the universe and everything. And the output range starts here. Okay, so now Excel produces a set of numbers with the characteristics that I want, mainly a mean of 175 and a standard deviation of 9. And you see we have entered them now into a table like this. Now we do the same for the valley people. We go again to data, data analysis, random number generation. But now I want still one variable, but now I want 30 observations. And I want a mean of 180. And I want a standard deviation of 8. And the output range, and I leave the seed, so if you replicate what I'm doing at home in your computer, you should see exactly the same numbers. But so now I'll start inserting those numbers beginning from cell C14, which is the first cell under the valley column. And then we just say OK. Okay, so now we have this fake data set that corresponds to those values. So now we can do, first of all, we calculate the mean. It probably will not be exactly 175 and 180, but very, very close. So the average for the mountain people is actually 173.97, and for the mountain people equals average okay. Well, okay, well, that's what it is. I wish the numbers would have been a little bit nicer, but well, that's what we got. But no big deal. So let's double check the variance. So that should be 81 for the mountain people. Okay, so let's highlight the 25 observation for the mountain people. Okay, so the variance is a little bit more than 81, it's 100. And the variance for the valley people that's actually 80. So Excel is probably not perfect for those kind of simulations, but just to illustrate how to test using the data analysis feature, that's good enough. Again, if you want to, we can also replicate again quickly the f-test and actually see what we get for those differences in variance, so that we can assume equal variance. So we use again the f-test formula. So I have to highlight the area 1, so that's the mountain people. Then we highlight the valley people. And then let's see, the probability is 40%. So that's still, we fail to reject that those are different variances. So we can assume safely that the variances are different. And so now if we want to just use Excel in order to conduct that test, we go to data analysis and we can safely go to sample, assuming equal variances, because we tested it. And then again, our data has labels, and then the variable 1 range. I highlight now the 25 mountain observations, including the header, and the 30 valley people, including the header for variable 2. The hypothesized mean difference is 0. And the output range, I put that maybe on top, somewhere like in cell D6 or so. Well, we should get slightly different values now. So we can see that the actual difference that we test for is not 5, or negative 5, but it's only negative 3.9. But what do we get? We get a pooled variance. Well, that is 89, which is a little bit higher. Ours was 71. The degrees of freedom, of course, that's correct. And we get the critical value. Well, that is the same. So the 1.674, that's the same critical one-tail test. And our t-stat, that is now different. Ours is like negative 2.1, but we had a wider gap. So the only thing that is the same with our example is the critical t. And of course the p-value for a one-tail test. Actually here we would fail to reject, because the probability of a one-tail test is that there is a 6% probability that we can observe the difference of negative 3.9 if there is actually no difference between mountain and valley people. But again, in our example of the problem set, we had a much wider gap. So that means the t-test statistic was much greater. Anyhow, so I just wanted to show you quickly how we can maybe simulate something similar to our problem set and how to use the data analysis tool for a two-sample t-test assuming equal variance. But it was just like a little bit of extra, which is focusing more on Excel capabilities rather than understanding a hypothesis test. All right, let's stop here and then let's continue with one more problem set about a two-sample t-test assuming unequal variance. But let's just stop here for now.